Welcome to the third session of this exponential and logarithmic function series. In this session, we will enhance your analytical skills to solve exponential and logarithmic equations as well as their inequalities through 11 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the third session of this exponential and logarithmic functions series. In this session, we are going to focus on both exponential and logarithmic equations as well as their inequalities through 11 worked examples. When watching this video, you may pause the video at any time and try the questions yourself. The first example is an exponential equation y equals 1/4 to the x minus half to the x plus 1, where x is between -3 and 2, including both endpoints. There are two questions asked here. The first one is to find the monotonic range over the domain. The second one is to find the range of this function. In order to simplify the analysis, we assume u equals half to the x because the base is half. So the increase of x results in the decrease of u and vice versa. Then the function becomes y equals u squared minus u plus 1, and its turning point form is u minus half, or in parentheses squared, plus 3/4. As for the first question, based on the given domain, u is between 1/4 and 8, including both endpoints. Since x is between -3 and 2, the corresponding u is between 1/4 and 8. Please note, when x increases from -3 to 1, the corresponding u decreases from 8 to half. Hence, y is a monotonic decreasing function when x is between -3 and 1. However, when x increases from 1 to 2, the corresponding u decreases from half to 1/4. Hence, y is a monotonic increasing function when x is between 1 and 2. As for the second question, based on the turning point form of y equals u minus half, or in parentheses squared, plus 3/4, y reaches its minimum 3/4 when u equals half, which is equivalent to x equals 1. Meanwhile, y reaches its maximum value 57 when u equals 8, which is equivalent to x equals -3. Hence, the range of the function is between 3/4 and 57, including both endpoints. Example 2 is to find the value range of a real variable a, given the inequality of a minus 3, or in parentheses to the -3/5, is less than 1 plus a, or in parentheses to the -3/5. Before analyzing this inequality, let's take a close look on the function fx equals x to the -3/5 first. Based on the rule of fx, the domain of the function is all the real number except the 0 point. Fx is also an odd function, which means fx is symmetric to the original point. The asymptote of fx is the line x equals 0. Hence, the function fx equals x to the -3/5 is a decreasing function when x is less than or greater than 0. Now let's come back to our question. Since the base on both sides of the inequality is different, we need to set them equal and calculate the critical value of a, which is -4. So when a equals -4, the left hand side equals the right hand side, which is not what we want. Now let's take a different value range of a to examine the inequality. When a is less than -4, obviously the left hand side is less than the right hand side, which is what we want. When a is between -4 and -half, the left hand side is greater than the right hand side. When a is between -half and 3, the left hand side is less than the right hand side. When a is greater than 3, the left hand side is greater than the right hand side. Hence, we may conclude from the above, the value range of a that satisfies the inequality is less than -4 and between -half and 3, excluding both endpoints. There are two sets A and B given in example 3. Each of them has two members and the 2 is their common member. The question is to ask the union of sets A and B. Since 2 is a member in set A, logarithm base 2 of the sum of A and 3 must be equal to 2. So from this equation, we obtain the value of A, which equals 1. Since A equals 1, the member B in set B must be equal to 2, because 2 is also a member in set B. Hence, set A contains 2 and 5, while set B contains 1 and 2. Therefore, the union of sets A and B is 1, 2, and 5. Example 4 is to simplify a logarithmic expression in terms of x and y, given that the common logarithm of a equals x and the common logarithm of b equals y. According to the given logarithmic expression, we applied logarithmic product and quotient rules to make it equal to common logarithm of 100 plus common logarithm of a cubed plus common logarithm of b to the -5/2. Then we substitute logarithm of a and logarithm of b by x and y respectively. Finally, the simplified expression is 2 plus 2a minus 5b/2. Example 5 asks us to solve two logarithmic equations. For the first equation, we apply the logarithmic product and quotient rules to simplify the equation and let both sides to have the common base. After further simplifying, we reduce the logarithmic equation to the quadratic form of 2 times x squared minus 9x minus 26 equals 0, which can be factorized and solved. So we obtain the results of x sub 1 equals 13/2 and x sub 2 equals -2. According to the logarithmic base numeral of x plus 2 must be greater than 0. X equals 13/2 is the only solution for this logarithmic equation. As for the second equation, we transform the exponential expression to logarithmic expression and make both sides to have the same common base. Accordingly, we have a quadratic form like logarithmic equation. Common logarithm squared of x plus common logarithm of x minus 3 equals 0, which can be factorized and solved. Hence, the roots of this equation are obtained. Here, x sub 1 equals 1/1000 and x sub 2 equals 10. Example 6 is to show the logarithmic expression of logarithm base a of b times logarithm base b of c times logarithm base c of a equals 1, given that constants a, b, and c are real positive numbers and none of them equals 1. Based on the given criteria, we change the base of all the three logarithmic expressions to 10. Of course, you may change to any valid base, but it has to be the same. After the base being changed, it can be seen that all the logarithmic expressions are cancelled out themselves, so it equals 1. In example 7, x is between 1 and a, excluding both endpoints. The question is a multiple choice question. Since x is between 1 and a, logarithm base a of x is greater than 0 and less than 1. Hence, logarithm base a of x is less than 0. Therefore, logarithm squared base a of x is less than logarithm base a of x, which is less than logarithm base a of x squared. Therefore, the statement of B is the correct one. There are three constants in example 8, as it can be seen that a equals natural logarithm of 2 divided by 2, b equals natural logarithm of 3 divided by 3, c equals natural logarithm of 5 divided by 5. The question is to make a comparison among a, b, and c, and it is a multiple choice question. Since 2 cubed is less than 3 squared, which implies that square root 2 is less than cubic root 3. Hence, natural logarithm of square root 2 is less than natural logarithm of cubic root 3. So, natural logarithm of 2 divided by 2 is less than natural logarithm of 3 divided by 3. Since 2 to the 5th is greater than 5 squared, which implies that square root 2 is greater than 5th root of 5. Therefore, natural logarithm of square root 2 is greater than natural logarithm of 5th root 5. Hence, natural logarithm of 2 divided by 2 is greater than natural logarithm of 5 divided by 5. Based on the above, the correct statement is C. C is less than A, which is less than B. Example 9 is to evaluate a logarithmic expression. After careful observation, we find that the base and base numeral of all the terms in the series are somehow related. Since logarithm base 2 to the n of 3 to the n equals logarithmic of 3 to the n divided by logarithm of 2 to the n, all the terms in the series are same. Hence, the original expression equals n multiplies logarithm base 2 of 3 multiplies logarithm base 9 of 2 to the fraction of 5 over n, which equals 5 over 2 after being simplified. Example 10 is to evaluate a logarithmic expression containing tangent values. According to the trigonometry identity relation, tangent alpha equals cotangent 90 degrees minus alpha, or in parentheses, which also equals 1 over tangent 90 degrees minus alpha in parentheses. Hence, common logarithm of tangent alpha equals negative common logarithm of tangent 90 degrees minus alpha, or in parentheses. Accordingly, common logarithm of tangent 1 degree equals negative common logarithm tangent 89 degrees, and common logarithm of tangent 2 degrees equals negative common logarithm of tangent 88 degrees, etc. Hence, the common logarithm of tangent 45 degrees is the only term remains because all other terms are cancelled each other. So the original expression is simplified to common logarithm of tangent 45 degrees, which equals 0. Example 11 is to evaluate an exponential expression 10 to the 2a minus b, given that 10 to the a equals 4 and b equals common logarithm of 5. Since 10 to the a equals 4, then a equals common logarithm of 4. Hence, 2a minus b equals 2 times common logarithm of 4 minus common logarithm of 5, which equals common logarithm of 16 over 5. Therefore, the exponential expression equals 10 to the common logarithm of 16 over 5, which can be further simplified to 16 over 5.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.